The main algorithm. First, we show how to initialize prices. So, the invariant holds. The following two conditions guarantee this. The initial prices are low enough prices that each buyer can afford all the goods. Fixing prices at 1 over n suffices since the goods together cost 1 unit and all EIs are integral. Each good J has an interested buyer, i.e. has an edge, incident at it in the equality subgraph. Compute alpha 1 for each buyer I, alpha I for each buyer I at the prices fixed in the previous step and compute the equality subgraph. If good J has no edge incident, reduce its price to Pj equals to the maxima of Uij over alpha I. Maxima is taken for all I. If the invariant holds, it is easy to see that there is a unique maximal tight set S which is a subset equals to A. Clearly, the prices of goods in the tight set cannot be increased without violating the invariant. On the other hand, the algorithm can raise prices of all goods in A minus S. However, we do not know any way of bounding the running time of any algorithm based on such an approach. In fact, it seems that any such algorithm can be forced to take a large number of steps in which it makes only very small progress toward decreasing the surplus of the buyers, thereby taking super polynomial time. Instead, we will show how to use the notion of balanced flow to give a polynomial time algorithm. The idea is to always raise prices of those goods which are desired by buyers having a lot of surplus money. Eventually, when a subset of these goods goes tight, the surplus of some of these buyers vanishes, thus leading to substantial progress. Property 1 of balanced flows provides us with a powerful condition to ensure that even as the network N of P changes because of changes in P, the algorithm can still keep working with a set of buyers having a large surplus. The iterative improvement steps follow the spirit of the primordial schema. The primal variables are the flows in the edges of N of P, and the dual variables are the current prices. The current flow suggests how to improve the prices and vice versa. A run of the algorithm is partitioned into phases. Each phase ends with a new set going tight. Each phase is partitioned into iterations that are defined below. A phase starts with the computation of a balanced flow, say F, in the current network N of P. If the algorithm of section 5.7 for finding a balanced flow terminates in case 1, then by lemma 5.2, the current prices and the allocations are equilibrium prices and the allocations, and the algorithm halts. Otherwise, let delta be the maximum surplus of buyers with respect to F. Initialize I to be the set of buyers having surplus delta. Let J be the set of goods that have edges to I in N of P. The network induced by I union J is called the active subgraph. At this point, we are ready to raise prices of goods in J. However, we would like to do this in such a way that for each buyer I in capital I, the set of goods she likes best, which are all in J, remains unchanged as prices increase. This can be accomplished by raising prices of goods in J in such a way that the ratio of any two prices remains unchanged. The rest of the algorithm for a phase is as follows. Step: multiply the current prices of all goods in J by variable x, initialize x to 1, and raise x continuously until one of the following two event happens, observe that as soon as x greater than 1, buyers in B minus I are no longer interested in goods in J, and all such edges can be dropped from the equality subgraph and N. Event 1. If a subset S, which is a subset equals to J, goes tight, the current phase terminates and the algorithm starts with the next phase. Event 2. As prices of goods in J keep increasing, goods in A minus J become more and more desirable for buyers in I. If, as a result, an edge ij with I in capital I and J in A minus J, A minus capital J, enters the equality subgraph, see figure 5.4, add directed edge Ji to network N of P, and compute a balanced flow, say F, in the current network N of P. If the balanced flow algorithm terminates in case 1, halt and output the current prices and allocations. Otherwise, let R be the residual graph corresponding to F. Determine the set of all buyers that have residual paths to buyers in the current set I. Clearly, this set will contain all buyers in I. Update the new set I to be this set. Update J to be the set of goods that have edges to I in N of P. Go to step. To complete the algorithm, we simply need to compute the smallest values of x at which event 1 and event 2 happen, and consider only the smaller of these. For event 2, this is straightforward. We give an algorithm for event 1 in the next section.